Hello, I'm Maurice Dupre, and in this section we're going to discuss extreme values of functions. Let's look at the definition. Let f be a function with domain D. Then f has an absolute or global maximum value on D at a point C if f of x is less than or equal to f of c for all x in D, and an absolute or global minimum value on D at C if f of x is greater than or equal to f of c for all x in D. So in other words, for the global or absolute maximum, f of c, notice it's the largest value. And for the global or absolute minimum, f of c is simply the smallest value. So let's look at a picture here. Suppose I have a graph that looks like this. Well, notice right here, that is the largest value. Way down here is the smallest value. So if that's the x-axis right here for this c, f of c is the global or absolute minimum, whereas for this value of c, f of c would be the global maximum. Well, in many applications, finding the absolute or global maximum of a function or finding the absolute or global minimum of a function can be very useful. We call these the extreme values of the function. If f is continuous on a closed interval a comma b, then f attains both an absolute maximum value capital M and an absolute minimum value little m in a comma b. That is, there are numbers x sub 1 and x sub 2 in a comma b with f of x sub 1 equals little m, f of x sub 2 equals capital M, and so therefore little m is less than or equal to f of x is less than or equal to capital M for every other x in the closed interval AB. Well, notice what this means. If f of x is your profit function, then the value you want is the capital M. And so consequently, this theorem is telling you there is an input x2 in the function which will give you that capital M in profit. Or if little f is the cost function and we want to minimize it, what this theorem tells us is there is an input x1 which will give us the minimum cost. So this is a very valuable theorem in that it tells us that some very useful things can be found. Well, our extreme value theorem tells us that for continuous functions on closed intervals, extreme values exist. We can find the global maximum and we can find the global minimum, but actually finding it, now that's a problem. So in order to do that, differentiability helps. Let's begin with a definition. A function f has a local maximum value at an interior point C of its domain if f of x is less than or equal to f of c for all x in some open interval containing C. A function little f has a local minimum value at an interior point C of its domain if f of x is greater than or equal to f of c for all x in some open interval containing C. In other words, what that means is if I restrict attention to some open interval containing C, if I can find it suitably, then f of c will be the global maximum of f on that little interval. And likewise for the local minimum, what it's saying is at the point C, I can find some small open interval about C such that on that open interval, f of c is the global minimum. So let's look at a little picture here. Suppose I have a graph which looks like this. Notice that right here I do not have the global maximum value of this function, but if I look at a little piece of the curve, if I restrict attention to a small piece, then that point right there is the global maximum. Let's look at this piece. Right here, I do not have the global minimum for this function, but if I restrict attention to this little piece of the curve, it is the global minimum. So in effect, when we're talking about local maximums and local minimums, we're talking about the same thing, except restricting our attention to small pieces of the curve. One thing we can notice now when we throw differentiability in is, in these cases, the tangent line at each one of these local minimums and local maximums, the tangent line is horizontal. So if our problem were to find the global maximum, we can see from this picture that if the function were differentiable at every point in its interior, then we could simply look for places where the derivative is 0 and then check values at the endpoints. Well, let's look at the theorem which guarantees that. If f has a local maximum or minimum value at an interior point C of its domain, and if f prime is defined at C, then f prime at C equals 0. An interior point of the domain of a function f where f prime is 0 or undefined is a critical point of f. So let's consider this in a little more detail. Remember, we just observed that for a local extreme value, we would have a horizontal tangent line. Well, that assumes that the derivative exists, but notice right here I have a vertex. The derivative does not exist there, the derivative does not exist there, the derivative does not exist there. So those are also local extreme values. Now our maximum on the whole domain, if the domain is a closed interval, will have to either be at one of these local maximums or at the endpoints. So now our strategy for finding the global maximum, global extreme values, both the global maximum and global minimum, is simply to look at the function, and if it's differentiable on the interval, or differentiable almost everywhere, we compute the derivative, find out where all the places are that the derivative is 0, find out where all the places are that the derivative is undefined in the interior of the domain. Then we check endpoint values and values at each critical point. Notice the biggest value and the smallest value among the critical values and the endpoint values will be the global extreme values. Well, let's use our theory of critical points and critical values to do some graphing and find extreme values. Here I have the function f of x equal x squared minus 1 on the interval -1 to 2. -1 less than or equal to x less than or equal to 2. So what we would like to do is graph this function on this interval and find its critical points and the extreme values. So in other words, to begin, we'll compute the derivative. F prime of x is 2x. Will that ever be undefined? Notice 2x, the expression makes sense for all real x. So in particular, it makes sense for every x in the interior of the interval from -1 to 2. So there aren't any critical points that come from the derivative being undefined. How about where the derivative is 0? Well, let's set this expression equal to 0 and solve. Notice the only solution is x equals 0. So x equals 0 is the only critical point. So that's a place where the derivative is 0 and therefore has a horizontal tangent. Well, let's consider the graph of this function, f of x equal x squared minus 1. We recognize right away that that's a parabola that's been shifted down 1 unit. So that's very easy to graph. Here's our interval -1 to 2. And the part of the parabola we're dealing with, we'll start here. When I take x equal -1, we get 0. When x is 0, we get -1. And then when x is 1, we get 0 again. And when x is 2, 2 squared is 4 minus 1 is 3. So we're up here at about 3 units. And so there's our graph. Notice right here at x equals 0, we have a horizontal tangent. That's our critical point, our only critical point. What are our end values? At -1, we got the value 0. So there's -1 comma 0 on the graph. Over here at the right end point, the coordinate of that end point on the graph is 2 comma 3. And of course, at our critical point, the coordinates are 0 comma -1. So for the values, among the values we have, the smallest is -1. So we can see from this -1 is the absolute minimum. How about among the values, what's the biggest? That happens at the right end point, and we see the biggest value is 3. 3 is the absolute maximum. And what we've also found is where these occur. To get our absolute minimum value of -1, we put x equals 0 into the function. To get our absolute maximum value of 3, we put x equals 2 into the function. Well, let's graph a function and use the critical points to help find the extreme values. Here I have the function y equal the square root of the quantity 4 minus x squared, and I want to consider it on the closed interval -2 less than or equal to x less than or equal to 1. Well, when you see that expression, you recognize right away that in and of itself, that should be the semicircle in the plane of radius 2 centered at the origin, the upper half semicircle. And so we know that its graph is simply the upper half semicircle. And so when we restrict to the interval -2 less than or equal to x less than or equal to 1, we're taking the part of this graph that just comes over here right over x equals 1. And so the graph over this interval is going to look roughly like this. Notice our picture's showing we have a horizontal tangent right there at x equals 0. That should be our critical point, and it's obviously the largest value. In other words, to make this biggest, clearly you want to subtract nothing from the 4, and if you do subtract nothing, you get square root of 4, which is 2, the maximum value. The minimum value is obviously here at the left end point. Well, let's calculate the derivative and verify that that is the case. dy dx is 1 divided by 2 square root 4 minus x squared multiplied by the derivative of what's inside according to the chain rule, which is -2x. And so what we have is -x, after we cancel 2's, divided by square root of 4 minus x squared. Notice this is undefined at x equals -2 and +2, but of course +2 isn't in the domain, -2 is. So what's happening there is our tangent line right as we come into the endpoint is becoming vertical, which is causing the derivative to be undefined at the endpoint. But as far as the interior values are concerned, the derivative is defined everywhere, and so the only critical point is where it's 0. Well, notice the only way it can be 0 is for the numerator to be 0, and that gives value 0. So consequently, the value dy dx will be 0 at x equals 0 and only then. So the only critical point is x equal 0. At that critical point, we see we get the maximum value. The value at the critical point is 2. So drawing this graph to a little larger scale so we can see it a little better, it would look like this coming up here. And here at this left end point where our global minimum occurs, the coordinates are -2, 0. And at this point where the maximum occurs, the global maximum, we have the coordinates 0, 2. So our absolute maximum is 2. Our absolute minimum is 0. Be aware that when you're looking for extreme values using the critical point theory, keep in mind some of the critical points can be where the derivative does not exist in the interior of the domain of the function. F of t equals 2 minus the absolute value of t on the interval -1 less than or equal to t less than or equal to 3. So we want to graph this function. Well, notice that for t greater than or equal to 0, absolute t equals t, whereas for t less than 0, absolute t is -t. So I can write the function this way. F of t equals 2 minus t for 0 less than or equal to t less than or equal to 3, whereas it's 2 minus -t, which would be 2 plus t, for -1 less than or equal to t less than or equal to 0. When I write it like this, you see the expression that's valid in the interval 0 to 3 is an expression for a straight line with y-intercept 2 having slope -1. And so consequently, we can easily draw that graph. It's simply going to be a straight line segment going down like this, and right here at 3, you can see is at x equals 3 is where it's going to hit its minimum, and the maximum value it has is right here at the origin x equals 0, and that would be 2. When I look at this expression, I have a straight line with y-intercept 2, slope 1. And so from -1 to 1, it's that little straight line segment. So there's our graph. Notice you can see that I have a vertex on this graph right at x equals 0, so the derivative should not exist there. Well, in order to make this clearer, let's rewrite the function in another way. F of t equals 2 minus the square root of t squared. Remember, the absolute value of t is the square root of its square. When I write it in this form, I can differentiate with the chain rule. The derivative of 2 is 0. We get negative of the derivative of the square root of t squared. Well, that would be 1 over 2 square root of t squared times the derivative of what's inside, 2t. Notice what happens. The 2's cancel. We have the negative out front, and so we get -t divided by square root of t squared, but remember that's the absolute value of t. So here we have our derivative, and notice it's going to be undefined at t equals 0. I have an expression in the denominator here which will vanish if t is 0. Notice what we're getting here. If t is positive, the denominator is simply t, the t's cancel, and we get -1. If t is negative, absolute t is negative t over negative t is +1. And that's exactly what our picture shows. And so what we see here is that our derivative is undefined at t equals 0. T equals 0 is critical because as f prime undefined at t equals 0. Well, let's practice finding critical points and local extreme values for functions. Here, I have the function y equal x cubed plus x squared minus 8x plus 5, and I want to find all the local extreme values and where they happen. So that means what I want to do is differentiate and set the derivative equal to 0, solving to find where every place is where the derivative is 0, and as well look for places where the derivative is undefined. Well, we see that's a polynomial, so it's differentiable everywhere, and consequently we're just looking for places where the derivative is 0. So dy dx equals derivative of x cubed, 3x squared, plus the derivative of x squared, 2x, minus the derivative of 8x, which is simply 8, plus the derivative of the constant, which is 0, and there's our derivative. And now this, to see where it's 0, we could factor. If you see how to factor this, do it. If you do not see how to factor, then simply go right to the quadratic formula. In any case, this one can be factored, x plus 2 times the quantity 3x minus 4. And so when we see that factorization, we see right away the only places where the derivative can equal 0 is at x equal negative 2 or x equals 4/3. So our only critical points are x equals negative 2, x equals 4/3. Now, when we compute the values, we find f at negative 2 is 17, and f at 4/3 is negative 41 over 27. And so here we have what appears possibly to be a local maximum that's certainly big, and here we have our other local extreme value, negative 41 over 27. Sometimes the extreme values of a function, including local extreme values and so forth, are just referred to as extrema. So let's look at an example finding the extrema of a function. Here I have the function y equals x divided by the quantity x squared plus 1. Of course, whenever you see a denominator, you always have to be wary of the possibility that some x value could make it 0. But notice x squared is always greater than or equal to 0 added to 1, will always be bigger than or equal to 1. So that expression is defined for all x. Now let's differentiate it and look at the derivative. So dy dx is, according to the quotient rule, well, the derivative of the numerator is 1 times the denominator, x squared plus 1, minus the numerator multiplied by the derivative of the denominator, all divided by the square of the denominator. Notice again we have the same expression here, except now it's squared, and so since the x squared plus 1 can never be 0, this denominator is never 0, and consequently our derivative is defined for all x. So we're not going to find any critical points on the basis of the derivative being undefined. What about the numerator? Here's an x squared minus 2x squared, and so consequently that will be a negative x squared, whereas 1 times 1 is 1. So we simplify and we find 1 minus x squared divided by the quantity x squared plus 1, all squared. Well, when I look at that simplified numerator, I see right away that it will be 0 if x is plus or minus 1. So our critical points are x equals plus and minus 1. Well, let's look at the values here. Notice the denominator is the same no matter whether x is plus 1 or minus 1, and consequently the sign is determined by the numerator, and when x is positive, it's positive. When x is negative, it's negative. In fact, when I look at this denominator being an even function and the numerator an odd function, I see this as an odd function. So if I look at its graph to the right then of x equals 0, I can reflect it back, turn it upside down to get the graph to the left. So at x equal plus or minus 1, our derivative vanishes. And when we look at that, what's going to happen is x goes to infinity. X over x squared is like 1 over x goes to 0. So we have a horizontal asymptote of 0 going both ways to plus infinity and negative infinity. So at x equal plus 1, our value is 1 divided by 1 plus 1, or a half. At x equal negative 1, our value is negative a half. And so consequently, this graph coming in from negative infinity asymptotically from the horizontal axis has a horizontal tangent line as I hit this point, negative 1, comma, negative 1/2, comes up. Obviously, at x equals 0, we get 0, and then it comes up here, hits this point with a horizontal tangent, and then goes out asymptotically to 0 as we go off to plus infinity. So clearly here at 1, comma, 1/2, we have the global absolute maximum value of this function, and here at negative 1, negative a half, we have the absolute minimum. Absolute max equals 1/2, occurs at x equals 1. The absolute minimum is negative a half at x equal negative 1. Well, let's find extreme values of a function in a case where we have fractional powers. When you see those, be careful. Here I have the function y equal x to the 2/3 times the quantity x plus 2. Notice that this actually makes sense for all real x. And when x is 0, the value is 0 because 0 to the 2/3 is 0. Whereas when x is negative 2, this factor vanishes. So this will be 0, y equals 0 at x equals 0 and negative 2. Now let's calculate the derivative. dy dx is, according to the product rule, 2/3 x to the negative 1/3 multiplied by the second factor x plus 2 plus x to the 2/3 times the derivative of the second factor, which is simply 1. Now notice in this expression I have fractional powers, but one thing that's useful to do here is to sort of consolidate the fractional powers. If I multiply top and bottom throughout by x to the 1/3 power, what I then have is the entire expression divided by x to the 1/3, and then multiply the whole thing by x to the 1/3. So x to the 1/3 times x to the negative 1/3 is simply 1. So we have 2/3 times the quantity x plus 2 plus x to the 1/3 times x to the 2/3 is simply x. Notice how the numerator has become very simple now. Let's get common denominators here, and I'll just absorb this 3 down in the denominator, and so we have 2 times the quantity x plus 2 plus 3x, all divided by 3x to the 1/3. Now simplifying the numerator, 2x plus 2 is 2x plus 4, 2x plus 3x is 5x. So we have 5x plus 4, finally, all divided by 3x to the 1/3 power. Notice when we have a denominator, there's a signal. Look to see where it's 0. And where that denominator is 0, our derivative will be undefined. Notice that's at x equals 0. So we have a critical point at x equals 0. So critical, right off, x equals 0. Now, where will the whole expression equal 0? That's where our derivative is 0. When the numerator is 0, well, that would be x equal negative 4/5. So now, when we look at an expression like this, x to the 2/3 times x plus 2, we've got two critical points, one on account of the derivative being undefined, and the point x equal negative 4/5, where the derivative is actually 0. Now, let's consider the sign of this derivative. If x is negative, then the 1/3 power is negative. So consequently, this denominator is negative to the left of 0. If my x here is less than negative 4/5, for instance, if, say, x is negative 1,000,000, then this numerator is negative. Negative over negative is positive. So consequently, this derivative is positive to the left of negative 4/5. And so if I just schematically were to draw a graph of this, here at negative 4/5, we're coming in with positive slope, so I'm going up, and then I must hit at 4/5 a local maximum, and then we go down, and here at x equals 0, our value is 0, and then the graph takes off again. There's the graph. It's got a vertex there at x equals 0, and so we have our local minimum is 0 right there at x equals 0, and we have a local maximum. Notice it's certainly not the global maximum at x equals negative 4/5. And if we calculate this, it comes out to be about 1.034. In other words, the value of y at negative 4/5 is about 1.034, giving that local maximum value there. Well, we've looked at our theory of critical points and the existence of absolute maximum and minimum values for functions defined on closed intervals. Now that you've seen these problems work, you should try some on your own. Keep in mind two things. First, when you set the derivative equal to 0, you have to calculate the derivative first. Do not forget to look for points where the derivative is undefined that are in the domain of the original function. That's a very, very important provision. A point in the interior of the domain where the derivative is undefined is also a critical point. If it's a point at the end of the domain where the derivative is undefined, it's still just an endpoint. But be careful to watch for points where the derivative is undefined. Second, whenever you're finding the absolute maximum and minimum for a function defined on a closed interval, after finding all the critical points and critical values, do not forget to check the endpoint values, because sometimes one of the extreme values can occur at the endpoint.